You flip a switch, and a light comes on. It's so simple, right? It feels like second nature. But what if I told you that our basic idea of how that all works is, well, mostly wrong? Yeah, so let's dive into one of the most fundamental forces in our lives and figure out what's really going on here.
Okay, to really get to the heart of this, let's start with this amazing thought experiment from the YouTube channel Veritasium. So picture this, a super simple circuit. You've got a switch and you've got a light bulb. They're just 1 meter apart. Easy enough, but, and here's the crazy part, the wires connecting them are insanely long. I'm talking a full light second long, like they loop way out into space and come all the way back. So, you close that switch. The question is, how long does it take for that bulb to light up?
You know, when Veritasium first dropped this question, the internet kinda lost its mind. Seriously, it sparked this massive debate. You had physicists, engineers, all sorts of smart people weighing in, and a lot of them were, let's just say, highly skeptical. The comment section was wild. People were throwing around accusations of misleading physics, even saying it broke the fundamental laws of causality. So, what on earth was the answer that caused all this drama?
Okay, so the answer that caused all that fuss? Get this. The bulb lights up almost instantly. It takes just the time for light to travel that 1 meter from the switch to the bulb, not the full light second it would take to go through the wires. I know, that sounds totally impossible. It feels like it breaks everything we know, but it's absolutely correct. And to understand why it's correct, we've got to first tear down a few common myths about electricity.
Look, most of us have these little mental shortcuts for how we think circuits work. You know, the classic water in a hose analogy? And hey, those are useful up to a point, but the problem is they're incomplete. And for a question like the one we just saw, they totally lead us down the wrong path. So let's get into it and bust the 3 biggest misconceptions out there.
All right, first up, myth number 1. This is the idea that electrons are like tiny little delivery trucks. They pick up a package of energy from the battery, and then they drive it all the way through the wire to the light bulb. It's a cute image for sure, but it's just not how it works.
Okay, so here's the reality check. Individual electrons are zipping around like crazy, bouncing all over the place at like 1,000,000 meters per second. But their actual forward progress down the wire, what we call their drift velocity, is incredibly, ridiculously slow. We're talking less than a millimeter every second. So the electron that actually lights up the bulb, it was already sitting right there inside the filament. It gets a jolt of energy locally from an electric field that pushes it, and that's what makes it glow. The energy comes from the field, not from some long-distance electron delivery.
And that leads us right into myth number 2, which is that famous marbles in a tube or water in a hose idea. You've heard this one, right? The idea that you push one electron in one end and it immediately shoves the next one, which shoves the next one, creating this instant chain reaction all the way down the wire. It feels so intuitive, but yeah, it's also wrong.
So why is it wrong?
Well, the most important thing to remember is that a normal wire is electrically neutral. See, for every single negatively charged electron, there's a positively charged atomic core sitting right there with it. So that push from one electron trying to repel another, it gets perfectly canceled out by the pull from a nearby positive ion. The forces just balance out. So no, electrons can't just push each other down the wire like a line of dominoes. Okay, so if it's not electrons pushing each other, it must be an electric field that's doing the pushing. And that field, it's got to come from the battery, right? I mean, the positive and negative terminals create a field. That makes sense. It seems totally logical, but this is actually our third and final myth. Just think about it for a second. The electric field from something like a battery gets way, way weaker the farther away you get. So if that field from the battery was the only thing driving the electrons, a light bulb right next to the battery would be super bright, but one at the end of a really long extension cord would be super dim. And we all know that's just not what happens, right? A bulb glows the same no matter where it is in the circuit. So there has to be something else creating that nice uniform field inside the wire.
And that's something else. Well, this is the real secret to how all of this works. It's something that's often not even taught in introductory physics. We're talking about surface charges. So what are these things? Well, the moment you connect a battery, a bunch of electrons on the surface of the wires, just the surface, rearrange themselves. And they do this almost instantly, at the speed of light. This creates this tiny charge gradient all along the outside of the wire. It's a little more negative near the battery's negative side and a little more positive near the positive side. And this incredibly clever arrangement is what generates a perfectly uniform electric field inside the wire, telling all the other electrons exactly where to go.
There's a really great analogy for this. Think of a shepherd, some sheep, and a bunch of sheepdogs. The battery? That's the shepherd.
It's providing the overall energy and saying, hey, let's go that way. The electrons are the sheep, just kind of wandering around inside the wire. And the surface charges, they're the sheepdogs. They position themselves perfectly along the path and create this local field of influence that guides the sheep exactly where the shepherd wants them to go. It's a perfect system.
Okay, so the field is the key, but that brings up an even crazier question. Where does the energy actually travel? And this is where things get truly mind-bending. The energy doesn't flow inside the wires with the electrons. No, it flows through the electromagnetic fields in the empty space around the wires.
And this is how we solve our original puzzle without breaking causality. The second you close that switch, you create a change. That change radiates out as an electromagnetic field at the speed of light, and it hits the bulb, which is only a meter away, almost instantly. Now here's the crucial part. That initial kick is totally local. For the first split second, the field makes the exact same thing happen in the bulb's wire, whether that long wire is connected a light second away or if it's totally cut. The bulb has no idea yet if the circuit is complete. It just feels the local field and reacts.
Physicists actually have a tool to track this energy flow. It's called the Poynting vector. And when you map it out for a simple circuit, what you see is incredible. You see the energy flowing out of the battery, traveling through the empty space around the wires, and then diving into the light bulb to get used up. The wires are just rails. They're guides for the field. But the energy itself takes the scenic route through the air.
Now look, this is an absolutely fantastic theory, but is it actually real? Can you prove it? Well, to settle it once and for all, the Veritasium team went to Caltech and built a real-life, scaled-down version of the experiment to measure exactly what happens in those first few nanoseconds.
And the results? They were absolutely conclusive. Just a few nanoseconds after they sent the pulse, exactly the time it would take for light to cross that 1 meter gap, the oscilloscope lit up. It measured a voltage across the resistor. And we're not talking some tiny little blip of static. It was a solid 4 volts.
So what does 4 volts actually mean in terms of power? Well, it translates to a power transfer of about 14 milliwatts. That is a real, significant, totally measurable amount of power getting delivered to the other side almost instantly.
And 14 milliwatts isn't just a number on a screen. To put that in perspective, that is more than enough power to get visible light from a modern LED. So the answer to that big thought experiment is a definitive yes. The bulb gets enough power to light up, and it does it way before any signal could possibly have traveled through all that wire. So what's the big takeaway from all this? It's that our simple models for circuits, Ohm's law, voltage, current, they're not wrong. They're actually incredibly useful tools. They work perfectly because they're describing the big picture result of all this super complex field behavior. But they also hide the deeper and frankly much more fascinating reality of what's going on underneath.
There's this veteran circuit board designer, Rick Hartley, who sums it up just perfectly. He says he used to think just in terms of voltage and current, but now he knows the real truth. His words, the energy in the circuit is in the fields. And for anyone designing high-speed electronics today, understanding how those fields move around outside the wires isn't just theory, it's absolutely critical.
And all this really leaves us with one final big question, doesn't it? We are constantly surrounded by this invisible world of fields. And if our understanding of something as simple as a light switch was this, well, incomplete, it makes you wonder, what other everyday things are we only seeing the surface of? It's definitely a good reminder to always stay curious.